Hi, my name is Heiko Kociolek and I'm presenting you rule-based code generation in industrial automation for large-scale case studies applying the CAYENNE method. And this is joint work with Andreas Burger, Marie Platenius-Mohr, Julius Rückert, Adil Abuquaik, Raoul Jetli and Abdullah PP. And we're all from ABB Corporate Research in Germany and India. In our work we have to deal a lot with automation projects for production plants, for process plants. For example, you see here a picture of a chemical facility, or we also look at oil refineries, pulp and paper plants, steel mills and so on. And these include a lot of automation equipment, including sensors, actuators and controllers. The controllers run control algorithms, and this software needs to be written by hand today. And the way the engineers design such a plant starts with schematic drawings where they capture their requirements. And these drawings are, for example, piping and instrumentation diagrams. Here's an example of such a diagram. The large column shapes, for example, are tanks for some fluids or gases. Then we have these circular shapes are sensors. They measure, for example, temperature, flow, pressure, and the level in the tanks. And then we have also actuators. The butterfly shapes are valves, and then this circular shape here is the pump. And this captures the automation requirements for this plant segment and can then be used to create also the control logic for such a plant segment. Our idea is to do a rule-based code generation. Today, for an automation project, you may get dozens of P&I diagrams, even hundreds of them. And they are mainly manually processed, usually exchanged via a PDF file or printout, and the control logic implementation starts by manually interpreting those diagrams, and at the end we get ICSE 611 control logic as the output. Our idea is to turn this into an automated process, so we extract object-oriented topology models from the CAD drawings according to the DXP standard, and then we have a rule engine which processes the models and creates the control logic almost automatically. Here's a short running example to show the concept. We have this very simple topology model with a vessel, a pump, and two valves. And we have a rule which says if a vessel has a level sensor attached to it and there's a level sensor height alarm signal, meaning that the level in the tank is too high and the tank is about to burst, then close all the valves on pipes feeding the vessel. So in this situation, this rule would match here for this level sensor. The letter L indicates it's a level sensor. And then we can trace back here through this pipe number P1 and then back to the V102 and also back to the other feeding valve. And these instances could be then used to generate structured text, ICSE 611 structured text. So if the level sensor with this tag number raises a high limit, then we set the open signal for the valve to false and also for the other valve. We also developed a shorthand notation for the rules, which allows a streamlined specification of new rules, and essentially says the same thing: the vessel alarm level high, and the vessel is connected backwards to a pipe and then backwards to a valve, then close that valve. That can be instantiated through the whole topology model. This is how our topology editor for the CAYENNE topology model looks like, and it visualizes the topology models in a graphical user interface. You can see here the object-oriented entities it extracted: pipes, level sensors, controllers, and so on. You can also click on them and then see all their attributes, which include the graphical parameters, but also some properties that are relevant for the control logic generation. For example, here the alarm limits, which are directly specified in the diagram. We can then switch to our rule engine, and it offers you to open different rule files. We import the topology model, and then you see here 5 different rules with our special purpose syntax, which can be checked also for syntactical correctness so that the engine can process them. And that's what we can do with the parse button here. So this rule we selected is now applied on the model, and then a complex model traversal starts, going through the model and searching for the situation that are specified in the rule. For example, this level sensor B115 is now interlocked with the valve 101. We'll show that on the diagram here. This level sensor here, it interlocks with the valve so that the tank does not burst, it runs to full. But also the situation occurs 2 more times. Also the valve number 104 is interlocked with another level sensor, that's B114. And B114 is also interlocked with 102. You can also display the interlocks in a table. We executed 4 case studies to validate the CAYENNE method, and they are described in detail in the paper. There's some statistics here in this table. All in all, we analyzed dozens of P&I diagrams from these plants. Here's a photo of one of those P&I diagrams, and here's a photo of a whole set of 23 P&I diagrams we analyzed from one of the case studies. This table summarizes our results. So in general, we were able to generate a vast majority of the interlocks using our rule engine. On average, it was in the case studies more than 90%. And we classified 73% of the rules from these cases as generic. That means they could be applicable to other cases as well. 68% of the rules generated multiple interlocks, and in that case they are most effective, and it pays off to use a rule instead of directly specifying the interlock. Unfortunately, only 7% of the rules that we mined were applicable across the 4 cases that we have here, because the cases we analyzed were quite heterogeneous and didn't have a lot of similarities. That's why this is quite a low number. If you analyze more similar plants, this number could likely be higher. To summarize, I presented you rule-based code generation in industrial automation. We utilized object-oriented models derived from CAD drawings, and we created a rule engine that is able to generate up to 70% of the interlocking logic that is required for these plants, and that shows the automation potential here. These would be 70% of saved manual efforts. We mined more than 90 different rules from these cases, and we estimated that this can lead to a total effort reduction of 21% in such an automation project, which can be up to several hundred thousands of dollars. In the future, we also want to utilize the models for other purposes, for example, for simulations and for the generation of process graphics. Thank you for your attention.